Well, good morning, ladies and gentlemen. Glad to see most of you back. This is an important day because if ever you would like to know what the linear circuit is, you have to know what a nonlinear circuit is. And that's what I'm going to talk about today. Leading to several kinds of distortion. I can never cover all kinds of distortion because distortion is kind of a garbage bag where you put everything in there which is nonlinear. So I can't cover that. That would take a full day, but I'm going to cover the most important sources of distortion. So let's have a look at what I'm going to do. Well, distortion is mainly our concern because of mixing up of communication channels. Meaning that when you have a channel 1, and there is another channel 2 just next to it, that when the channel 2 is used, there is some information there, some sidebands, some other kind of information, that it's going to spread to the other channels. So we see that channel 2 is mixed into channel 1, meaning that in speech you hear some kind of sizzling coming from another speaker. On TV you have those lines coming from another channel, and each communication channel has some kind of a limit on how much modulation can be imposed from one channel to another. And that's caused by nonlinearities and some other things, so that's what we don't want. So the question is then, where is it coming from and what can we do about it? And there are some simple rules like feedback, for example, and some other ones. So we will have a look at how to do distortion to avoid cross-modulation, modulation from one channel towards another channel. So let's first define what kind of distortion we're going to talk about, and there are so many, like harmonic distortion, intermodulation distortion, intercept point, the -1 dB compression point, etc., etc. How do they relate and which one are we going to use? And then let's have a look at what a MOS does. A MOS device is a nonlinear device, square law, exponential, and so on. I can use a differential version, getting rid of all the even order distortion. And then I take bipolar too, because bipolar is exponential. Bipolar or a MOS device in weak inversion, and as you know we use more and more weak inversion, so that's important. Yes, let's use feedback to reduce distortion, and let's have a look at some more complicated circuits and the general rules for low distortion. First of all, I'm not going to talk about linear distortion. Isn't that a contradiction? Somehow yes. I can have a perfectly linear amplifier, but I can have some filter action in there caused by capacitances. And if I have capacitances in there, obviously the performance at higher frequencies or at lower frequency is going to be different. Meaning I filter out some components. If this frequency has harmonics, they are going to be reduced simply because of the filter action. That's called linear distortion. There is no generation of harmonics as a result of that. There is simply modification of them. So that means that each filter is going to give you linear distortion. The picture in time, for example, but also in frequency, if you don't have that, you would have a all-pass network. But all filtering gives you low-pass, band-pass, or high-pass filtering, and that's called linear distortion. That's not what I'm talking about. I've talked about filters last time, and I'm going to talk about filters next time. Okay, and they give you, on top of the nonlinear distortion, gives you linear distortion. For example, if I take something with a lot of harmonics, like a square waveform, which does not only have the basic frequency, but the second and the third and the fourth, etc., etc., clearly if I put that through a low-pass filter, I'm going to have something where the higher frequencies are attenuated, and the higher frequencies are in the steep slope here. They are attenuated. So this picture is different from this picture. That's linear distortion. So all filters give you linear distortion. Also, for example, when I take a high-pass filter, a high-pass filter would give you something where the high-speed edges get through, something like that, for example. Okay. So filters give you linear distortion. I'm talking about non-linear distortion today, meaning that I have a nonlinear output versus input characteristic. As you can see, this is nonlinear. But all of them can be very linear provided I take a very small swing. When I take a very small swing like this, then clearly when I take that small enough, it's going to be more linear. Meaning that when I take a very small swing like for small signals, it's going to be more linear. And the nonlinearity is going to get worse when I take larger swings. So that means that nonlinearity always increases for larger swing. And one of the rules is going to be later on, if I take a small current swing in a transistor, when the current only goes up 1%, for example, the distortion will be very low. And that is used in very low distortion amplifiers. You swing the current only over a very small fraction. I'll come back to that. This is just to show what we are talking about. Clearly we have a quiescent point, Q, which is set by some DC level. And when I swing the input voltage in a perfectly sinusoidal way, no distortion here, not much at least. How can you see that? You see distortion as soon as you have more than 1%. 1% is about the limit, which is nothing. Minus 40 dB is a lot of distortion. So normally you can't see that. So this is terrible. This is terrible. So when I put in a sine wave, I'm going to cover this range. I'm going to cover this range of the transfer characteristic, leading to something which is heavily distorted. Okay? And that characteristic will allow us to explain how much distortion we have in there. And clearly, the smaller the swing around Q, the lower the distortion, obviously. Now, I never go that far that I have a hard nonlinearity. I never go that far. Meaning that if I exaggerate and I go way too high, like for example with this amplitude here, I get a limit here, a hard limit. As soon as you have a corner in there, you get more than 10-15% distortion. I don't know any application which allows hard limiting. Most applications talk about minus 60 dB. Minus 60 dB in audio you hear very well. Minus 60, 70 is okay for speech in most communication channels. When we talk about images, when we talk about pictures like on TV, you always go to minus 80, minus 90 dB. So there's nothing you can see, okay? So that means that hard limiting is not acceptable. There's nothing accepting minus 10% distortion. So we are talking about low-level distortion, low-level distortion. And that means that we only cover a small fraction of this nonlinear characteristic, okay? And now how are we going to approximate this characteristic? I can have a closed loop expression like this, a square law expression, or an exponential, or a combination of those. I can have that, but I'm going to develop always a power series around the quiescent point. I'm going to describe this as a DC level, and then a linear characteristic for small signals, a DC level, a linear characteristic for small signals. This is the linear component, and the more I go up and down, the more I need more components to describe this nonlinearity here. And I use power series for that. So the first question is, how do I get the components of the power series from a closed loop characteristic? Well, the first one is an easy one. If I take the derivative here, if I take the derivative in the quiescent point, the first order derivative is going to give me A1. You may remember from before, the derivative in a point of a nonlinear characteristic gives you the gain if this is output versus input voltage, or the slope in this point. And the slope is A1. And then of course how they get A2, you take the second derivative and you take the third derivative, and we never go further because I'll show in just a moment. A2 stands for A4 and A6 and so on and so on. And this stands for A5 and A7 and A9. But we never go that far because they get smaller all the time. If you have a continuous characteristic, the higher order terms get smaller all the time. And A2 stands for all the even ones, and A3 stands for all the odd ones. So that's why nobody goes further than 2 and 3. And that's why we simply take the second derivative, but then we have the 2 up front. We have to take that out. And we take the third derivative. We have already second and the third, so we get 3 faculty, which is 6. Okay. So to find those coefficients in a power series is easy. You just take derivatives. Did I say easy? Many of those nonlinearities are equations like this. And to take the derivative is not easy. And sometimes in paper you find 1/3 of a page with one expression, the A3 for example, which could be very complicated. So only for simple nonlinearities you have a simple result. Yes? Is the microphone off? Is it off? But you are on the first row, you hear everything direct and okay. This is better. Maybe you should increase the volume a little bit, but I'm sure you can hear me and I hope they can turn up the volume. Thank you for the comments. Very important I do this right. So, A3 is sometimes difficult and I'll show you some equations which are terrible. Now, once you have the coefficients, whatever kind of distortion you talk about is going to be okay. I have harmonic, intermodulation, cross-modulation, all that stuff. Okay? So I'm going to, yes, once I have this, I can easily figure out harmonic distortion, because if I put in a sine wave, why do I call that a sine wave? It's cosine, because the trigonometry is a bit easier. The trigonometry, yes. Because if I put a sine wave in there with a amplitude, and I keep on getting the question, the amplitude is at RMS, is that peak to peak? Come on, you know that if I say my signal here is u cosine omega t, this is the peak value, isn't it? Don't ask me, huh? It's peak. So RMS is different, square root 2 times smaller, isn't it? So if I put that in there, in here I get a cosine square. Cosine square, what does that mean? I look up the tables in my book of trigonometry, or I still remember, that the cosine square gives me DC and 2 times the frequency. That's what it means. DC and 2 times the frequency. And the cosine third gives me the fundamental and 3 times. And cosine 4, what is that going to give me? Cosine 4. Cosine 4 is going to give me 1 and 2 and 4. I don't know the exact expression, I don't care. And cosine 5, what is that going to give me? That's going to give me a change in the fundamental. It's going to give me a bit of 3, and it's going to give me a bit of 5. I usually limit myself to DC, yes. If you have a second order term in there, the DC level is going to change. Okay, yes, if I overdrive a transistor, the DC, the average current will change, and I have second order harmonic, because everything I find in there with the half and the A2 is going to give me the second order distortion, second harmonic. It's simply the ratio of the coefficients. This is why I take a power series. It's so easy to calculate distortion. And the half, don't forget, and the U is in there because we have 2 of them there and only 1 there, meaning that yes, the amplitude is in there. Of course, the more you swing, the more distortion you get. Okay? And for the third order distortion, it's very simple too. I get A3 instead, but I get 4 because there is a 4 there, and I get U squared because I have 3 minus 1 is U squared. So this goes up much faster than this one. I can plot those second and third order harmonics, and I can do all kinds of calculation. I put in some numbers to remind you that peak is not the same as RMS. If, for example, I have a power series here with 10, and this is 1 per volt peak, and this is 0.4 per volt peak, we will do calculations on real transistors, of course. Then for a certain input voltage, and I put in values with dPs and peaks in there. I'm sure you can reconstruct everything here, I'm sure you can do that, and find RMS values with the square root 2, and sometimes we use dBs or dBms. 0 dBm corresponds to a milliwatt and 50 ohms. I'm sure, remember that corresponds to something like 0.23 volt RMS. Okay, so all those things are used, dBs and dBms, when you talk about distortion. And this slide is there to remind you how to do those calculations. They are not difficult, but if you do it, you all have different results, surprisingly. Now, simple calculation, here it is. How much would that be if you do the A2 and the A1? Well, of course, we have something like so much. You can see that. Or minus 36 dB, 0.1% is minus 6 dB, 0.1%, Easy, huh? Easy. Now I can plot them versus input voltage, and that's important. Most people don't. You should. Why is that? To see if you have the right slopes. Measuring distortion is difficult. As difficult as noise. It takes you days and weeks to do the measurements. And the first thing you have to check is whether you have the right slopes. If you don't have the right slopes, you measure something else. And there are so many things you can measure nowadays in the laboratory. There's so much in the air. Okay? So if you don't have the right slopes, you measure something else. Second order distortion versus amplitude. Log. Never log, linear would work too, but we would like to see that over a certain range. So you usually take log to figure out the right slopes. If you take log linear, you have exponentials. What can you say about exponentials or log curves? Here you have a slope 1, and there you have a slope 2. And that's the hard one, because if you go too high the level off, you end up in too much distortion. And if you go too low, you end up in noise. So this is quite often limited to a very narrow region of input voltage. That's why it's important to put that on a log slope to identify the slopes. Okay? So never plot distortion anymore on a linear curve or on a linear input amplitude or something. They do that in verification of equipment because it's easy to do. But to understand what you're doing, log. Okay? And you see both of them are very different. And if I find a trick like making every differential, when I make something differential, I take out everything that's even order, and then this one is the most important one. That's why most people only talk about third order distortion. I'll come back to that. And for an example, this is a measurement on a log plot of total harmonic distortion, which is of course a big mistake, because this one goes up with the amplitude and this one goes up with the amplitude square. So how can you figure out what you do? Well, you can't. If I take a curve like this, luckily for this simple example of a resistor, on the lower level here, I see that the slope corresponds to second order distortion. And on the high level, the slope corresponds to third order distortion. And when you take them separately indeed, you see that the second order distortion corresponds to this line, and the third order takes over at the high values and corresponds to this line. Total harmonic distortion in a scientific paper is nonsense, because you don't know what you see. Is it second order or third order? Okay? So you have to split them up and say something about that. If your circuit is not fully differential, but nowadays most circuits are differential, and this is the one which is dominant, but in older papers maybe it's not differential, we still make single-ended amplifiers, okay? And then you have both, and then look at total harmonic. Does not allow interpretation. Don't do that. Of course, an easier way is to have a look at the spectrum, the spectrum analyzer versus frequency, always on a log scale. That depends on how you look at it. And the ratio between those two, the second order distortion, and the ratio between those two, that's the third order one, is third order distortion. So, most people use intermodulation distortion, not harmonics. Why? Well, in intermodulation distortion, depending on the system, if you have a system with channels like TV, communication, etc., you take frequencies on two adjacent channels, channel 1, channel 2. But in audio, for example, you take 50 Hertz and 4 kilohertz in audio. So it depends a bit on the application. In sensors, it may be different again, sensors. Applied frequencies is a different thing. So in communication channels, you take two channels, channel 1 and channel 2, and they have the same amplitude. You could change that too. And then you put that one in there. Clearly, if you have cosine plus cosine square, what is that going to give you? That's going to give you two frequencies, the sum and the difference. Yeah. And if I put that cosine plus cosine third, what are you going to get? Whoops, that's a bit more complicated, You may not remember that from trigonometry courses. Then you get four components, 2 omega 1 plus minus omega 2, and 2 omega 2 plus minus omega 1. Where are all those components? clearly what you find on those, it's called second order intermodulation distortion. They depend on the same coefficients, so we are not surprised to see that we have the same ratio and the same U in there, but it's 2 times larger. Trigonometry. And the other one here is 3 times larger. But of course, when you take harmonic or intermodulation, they depend on the same coefficients. I get a similar story. So the first thing I have to show you is where all those components occur, and then you'll understand why we use them. So here is a graph where I have taken 2 channels. Channel 1, not channel 1 and channel 2, but channel 10 and channel 11. Let's take 10 and 11 megahertz or kilohertz or whatever. Those are the 2 fundamentals. And where are all intermodulation products? First of all, where are all the harmonics? Well, the harmonics for 10 are going to be at 20 and are going to be at 30. You see? And of course, the other one at 11 is going to be at 22 and at 33. And now you see where all the intermodulation ones pop up. First of all, for the second intermodulation one, second intermodulation is going to be the sum and the difference. And you see now why second order distortion is important in low frequency amplifiers like audio. If I have, which is now so easy with all kinds of synthesizers, if I generate 50 and 51 kilohertz, then I can easily have 1 kilohertz, which I can hear. I can't hear, certainly not me, I can't hear 50 and 51 kilohertz, but I can hear 1 kilohertz. So that's why in some amplifiers the range extends to frequencies which are ridiculous, simply because you don't want second order intermodulation distortion, which folds that back to lower frequencies. Okay? That's for second order. And now for third order, we see 4 of them. 1, 2, 3, 4. Now clearly the important ones are those. They appear in the channel one higher and one lower. They are the important ones. If I apply a filter, for example, which I usually have somewhere, something like this, then all this is gone. But I still have those. That means that third order intermodulation distortion is the most important kind of distortion for all communication systems, or all systems where you have a lot of frequencies adjacent to each other. Because third order intermodulation is hard to get rid of, because it comes with a fundamental. It's not like the second order one that I can cancel in the differential circuit. I can't cancel it. So that means that it's going to appear right next to the 2 channels, one there and one there. That's why in all those transistor circuits, we talk about third order intermodulation circuits. The second reason why it's important, is that intermodulation is 3 times larger than harmonic distortion. And remember, there was a 3 there, 3 times larger. It's difficult to measure, so we are very glad to see that this is bigger than this one here. That's the second reason. But the most important reason is, of course, that they are present very close in the same frequency region as the 2 fundamentals. So we are going to talk all the time about IM3, okay? Mainly because for second order we make a differential and it's going to cancel out. And third order harmonic may be filtered out somewhere, and we are only left with third order intermodulation. Okay? So once we have the power series, and we know A3 and we know A1, I can figure out 3/4 of that depending on the amplitude peak, amplitude peak, I can figure out the IM3. Okay? Now this is an example of a measurement to show you how risky a measurement can be. Because it's easy for me to say, well, this is my fundamental, that's obvious, that's another fundamental. Let's see where it was, 10.7 megahertz, an IF amplifier somewhere. And you see that on the same distance we have this one, this is clearly IM3. And on the same distance we have that one, this is clearly IM3. They are not the same. This is a little bit smaller than this one. We have some kind of At low frequencies you would call that a baseline drift or something, and you see some other peaks. I don't know what that is. Some intermodulation somewhere else. I don't care about those. Those is what I care about. Okay? So it's not always easy to figure out where they are, but on equal distances it's easy. And the other ones, I don't know what that is. Okay? Now we have a few more ways to characterize distortion. You would think that everybody quotes IM3 in his paper? No. No. They say something else. They say my IP3 is so much. What is IP3? IP3 is actually the IIP3. The intermodulation, the third order intermodulation intercept point. And this is simply the extrapolation. This is my gain. This is input, log scale, log scale. This is the gain, huh? And this is my third order intermodulation component. And when I increase this one, this increases much faster. This is first order, and this is third order, huh? And of course, at some point they are going to meet. A point which you can never reach, of course. By the time you are there, everything is leveling off, large amount of distortion. But I can draw a line, and that point where they meet, the input voltage where the two meet is called the IM3 intercept point. Some people call that IIP3, and most people call that IP3, because IIP3 is kind of strange. Huh? So we call that the IP3, usually expressed in dBms or in numbers or something. This is the input voltage for which you would have those two coinciding, if you could go that far. And the nice thing about that is that it includes everything else. So now I don't have to quote IM3 anymore, which I have to quote at a certain input voltage, of course. IM3 doesn't make any sense unless you say where you measure it. Some papers leave that out. They say I have so much distortion, IM3. It doesn't mean anything unless you know where it is. Huh? Because when I go higher, it gets smaller, and when I go lower, it gets bigger. Sure. And the IP3 says it all. Because once I know IP3, I can calculate IM3 at any value. Okay? So IP3 is useful. Some other people say, well, this is too hard to measure. I'm going to take the point where my input signal goes down by 1 dB. Not so accurate, huh? My input signal goes down by 1 dB. That means indeed, don't forget that when I look at third order distortion, huh? Third order distortion changes the fundamental as well. When I have a lot of third order distortion, it changes the fundamental, goes down a little bit. So there must be a relationship between the minus 1 dB compression point and the IP3. It's not so accurate because minus 1 dB is not that much. Huh? I'll show you in just a second that this is about 10 dB from the other one. Many people quote both, and yes, it's about 10 dB. It's sufficient to quote one. Huh? We all know it should be 10 dB. Okay? So the minus 1 dB compression point is not so easy to measure. We prefer IP3. And is this the nicest number? Well, that number gives you how much IM3 you have at this voltage. It also gives you the maximum you can get, because this is the maximum range that you can get. This is called the intermodulation free dynamic range, because if you go lower, you're taken up by the noise. So if you go lower your dynamic range, your signal to noise ratio goes down. So the nicest number that you can quote about an amplifier or filter, the number all designers should quote in their papers, is the intermodulation free dynamic range, this number, or the IP3 and the noise level. Because if you have the noise level and the IP3, you can calculate the intermodulation free dynamic range. Huh? So those are the numbers we are going to use now. All those filters I'm going to talk about, also the ones I talked about last time, the switch capacitor filters, we should have quoted the IMF, the intermodulation free dynamic range, but it's only now that we talk about distortion. So next time when I talk about continuous time filters, all of them have a number like IMF, DR3. They should have a number. Is that used in papers? No. I'm already very happy if they quote IP3, and I'm already very happy if they quote noise. So you can calculate this number and do a comparison. Okay? So now the relationship between all those numbers is easy. Not easy for the calculation, but easy to look at. For example, this one here, the IP3 is simply where those two get together. Clearly you have the ratio in there. Clearly, this is much bigger than this one. Okay, the 4/3 is in there again, the square root. The IP3, because remember this one goes up with the square compared to this. That's why there's a square root. This is a number, huh? Is this a number? No, this is a voltage. Be careful. Volt peak, volt peak, volt peak. Don't mix RMS and peaks. It's a number. If I have the number, the voltage, if I have a certain voltage here, V in, I can take the IM3 at that point, and that's the same thing, huh? Okay, I can do that in dBs, of course, dBs, obviously. Okay, I can take the IMF if I have the noise, noise level, noise in microvolts, not per square root hertz. Eh? If I have a noise level in volts, and this is also volt, then this is going to be the modulation free dynamic range, third order compared to all this, or 2/3 of this and that. If you have the IP3 and you know how much noise you get, this is in volt and this is in volt. Both in volt RMS or both in volt peak, I get 2/3. Or in dBs, it's 2/3 in dBs. Okay? It's a golden exercise to try it once yourself with all those numbers. Because if you take, for example, power instead of volt, then it's only 1/3. Huh? If this is power instead of volt, then it's only 1/3. Huh? What number do you get in the paper? Is that power or is it volt? That makes it difficult to put those numbers together. Okay? You'll have to learn to do that if you're interested in distortion. Here is a simple example again. The numbers are right now. There was a mistake in there in the original Blue Book version. 10.4. I don't care about A2, it's a differential filter. Huh? And I put in 0.3 volt peak in there, corresponding to 0.22 volt RMS, corresponding to minus 10 dB volt peak. Yeah, dB volt is used as well, huh? Compared to 1 volt, dB volt compared to 1 volt. Volt peak, you have to put volt peak or RMS, you can have minus 10 volt dB volt RMS, isn't it? You take 1 volt RMS as a reference and you take dBs with respect to that. You become an expert in dBs when you do all this. Huh? Or 0 volt dBm, this corresponds to 0 volt dBm. Yeah? And here it is, here are the values. 5.8 volt peak of 4.1 volt RMS. And then for so much noise, 300 microvolt, this corresponds to a filter I'm going to use next week. 300 microvolt, I get an intermodulation free dynamic range in volt of so much, in power of so much. Those are numbers, huh? This is a number, no dimension. Everything is volt, okay, but this is a number. This is a number, nothing else. This is a number, just a number. And you're welcome to put that in dBs or whatever you like, huh? Okay, and here it is then. If I calculate in a modulation free dynamic range in dBs, I get 55 dB. You should try that once, those numbers, and see whether you can have those 55 dBs coming out of there. It's not easy. Much more difficult than noise calculations. Okay, those are the right numbers. Now it's time we do something more on transistors. Huh? I keep on talking how to carry it. Minus 1 dB is of course multiplying by 0.9, not quite 0.9. Minus 1 dB is about 0.9, and then I can calculate this corresponds to about 10 dB difference. If I have the IP3 here, okay, then this is about 10 dB, huh? That's what this says. Okay, and I can calculate that for the previous example. Sure. Something else I can use? Well, no, that's it. And why IM3? Because actually it's IM3 that I use to calculate the cross modulation. If I know IM3 and I use a modulation index for this kind of modulation, the modulation index, how deep I am with my sidebands, multiplied by IM3 gives me cross modulation. That's why IM3 is the thing to focus on. Okay? Now let's do that for a MOS device. Finally, a transistor. What is the IM3 for a MOS transistor? A MOS transistor can be very simple. It's no more, but it was simple. It was just a square law characteristic. Now it's a combination of things. If it is square law, of course it's easy to figure out if I apply a voltage with a DC component and an AC component. I'm going to have a DC component and an AC component. Now this is DC and this is AC. How do I know? Well, this is capital, this is not, and this is small lowercase, this is higher case, lowercase. So that means that we have to distinguish between DC and AC. And AC like this is a AC component only. If I take lowercase with large values, this is DC plus AC. And this is, for example, the amplitude of the AC component. It's easier to see what I'm talking about when I look at this. Meaning that if I look at the total value of a signal, then it's this one. You see, it's I with the dot DS, capital letters. But if I look at the AC component only, it's lowercase I, lowercase ds. This is the DC component only. The other one is the whole thing. Okay, and then of course I can have a peak value of an RMS value, and then we have this. Okay, or a Fourier transform. Okay, so you have to be careful how you write things, otherwise you can't talk about a distortion. Okay, so meaning that relative current swing is a quantity I'm going to use. Relative current swing is how much you swing with respect to the average value. How much I swing in peak value divided by the DC or average value. This is the peak relative current swing. And that's going to be the measure for distortion in whatever circuit. Relative current swing. How much I swing my current up and down. Okay. So I'm going to use that later on, but now I just want to make sure that if you talk about it, and this is not this is corresponding to IEEE rules, of course. So if you make a paper on distortion, you better respect that. You get everything back. So for example, to call a supply voltage something like this, to call a supply voltage something like that is ridiculous. This is an AC component on your supply voltage. That's good to calculate power supply and rejection ratio, but your DC supply voltage looks like this. Looks like this. This is only the AC component on your supply voltage. You don't always talk about that. Okay, so you have to be careful. Now here it is, the MOS transistor. Finally, our first device is a beautiful device. It has a simple characteristic, and yes, if you take an old MOS transistor, let's say 0.35 micron, 0.7 micron, there is a wide region where you have a pure square law characteristic. And if you have a pure square law, DC, AC, I'm only interested in the AC component. I'm only interested in the AC component. So I subtract DC from everything. And what's left is, of course, how much current I get as a result of the input voltage. AC voltage, AC current. Small single voltage, small single current. And this, we know what that is. And that should be GM. And we have calculated GM a zillion times in the beginning, which is, of course, the derivative of this expression. Sure, we knew that. But this is what's left. And what's in the third order one? Where is my third order one? Oh, come on, you know that. You can't have a third order component out of a second order equation. It's zero. That's the beauty of a MOS transistor. We have zero third order intermodulation distortion. This is why already 50 years ago, 40 years ago, we were looking for square law characteristics as a first transistor in a receiver. It would not generate third order intermodulation. Beautiful. Only second order. But of course it's only for a pure second order expression. Pure second order expression. So if I rewrite that in terms of coefficients, G1, G2, G3, this is 0, that's obvious, and the second order one is like this. And it says indeed that your input voltage is scaled by Vgs minus Vt. If I make Vgs minus Vt larger, then this distortion is going to be smaller. We have tried to make Vgs minus Vt small, to have a larger GM over I, remember, a long time ago. to have more GM coming out of there. Well, the more you do that, the more distortion you get. You have to make up your mind what you want. Huh? Everything that helps gain and GM is bad for distortion. Okay? IM3 is 0, and that's the beauty. The early receivers used MESFETs and gas FETs and indium phosphide FETs. Those exotic FETs in different materials are still square law. That's what we like them. And if you only have one transistor for a real high frequency receiver, a satellite receiver or something, then you don't have third order modulation distortion. Beautiful, huh? Now we are going to use, rather than to use expressions like this, we are going to use as a measure relative current swing. So what I'm going to put in there is put in the AC current and the DC current. So the AC current and the DC current, I call that relative current swing. And at the end of all your notes on the last pages, you see a table which summarizes everything I have to say about distortion. I'm talking about relative current swing. So the only thing we will have to do at the end is to figure out in the whole circuit, if I apply a little signal, where is the relative current swing the largest? And that's where you generate the distortion. Because you cannot make closed loop expressions on a full amplifier. The only thing you can do on a complicated circuit like in those filters next week, where is the relative current swing the highest? And that's where you get the distortion. So we are interested in this expression. And for a simple transistor, very simple, huh? That means the relative current swing is nothing else than the VGS divided by VGS minus VT over 2. It's like GM VGS, that's the GM, reverse GM. And that goes in there, and that goes in there, and this is the final expression. U is the relative current swing. If this is 0.1, this is 0.1, this is 0.01, then 1/4 divided by this gives you distortion. Okay? So that's what we're going to use. For example, for 100 millivolt peak, that's a lot. So you better take a large VGS minus VT for this simple example. Then we have something like the peak value 100 millivolt, 2 times this and 1 volt is 0.1. So we have 10% in the modulation distortion corresponding to 5% harmonic. You can see that. Yes, that's a lot, and this is 0. And the current swing is 0.4. People interested in distortion never take a current swing of 40%. You have a DC current and it goes up and down 40%. That's enormous. When you're interested in distortion, you never go higher than 10%, 5%, 2%, 1%. Depends on what kind of a spec you would like to have. This is terrible, minus 20%. This is terrible. This is terrible. Okay. Now, of course, unfortunately, our MOS transistor is slightly different. We are hoping to have, where is the one I just discussed? Here is the one I just discussed. And you see, life is a little bit more complicated. Because, yeah, we have weak inversion on one side. We have velocity saturation on the other side. And they get closer all the time. In a 45 nanometer transistor, you don't see the square law region anymore. So what do you get? You get everything. You see that versus VGS, you have this one here saying that you don't have a square law region anymore. And then, of course, if I change not only the VGS, because I can change the drain voltage as well. Sure. And you know that versus drain voltage, we have an output resistor. That we know. And is that output resistor really linear? I'm not so sure. So maybe if it's not really linear, changing the drain source voltage, which is usually the case because you have gain, voltage gain. Huh? Maybe there is something there and maybe there is something there. And then, don't we have a VBS? I know you don't want to play with VBS, but more and more people seem to like that. I've said already 10 times, don't. Because if you play with VBS, you have a nonlinear GMB coming in with its own coefficients. Now, if all three of them are playing, then of course you have correlations between those two as well. You can have 2 of those, or you can have 3 of those, and then you have this. So if you really want to know everything about one transistor, you should know all those coefficients. Nobody has done that except for one person, Piet van Bak, and then he wrote a book that's thick about it. Of course, if you have all those coefficients, you better do something about it. Okay? But you have to know as a designer which ones are going to kill me. That you can rule out. Huh? That's one. This one, it depends. Huh? How nonlinear is your output resistor? Is that documented somewhere? I'm not so sure. This is an easy one. This is an easy one. If you are fully in square law or fully in the exponential region. If you follow my advice to go for inversion coefficients 1, then you know that you are exactly halfway a square law characteristic and an exponential. So how are those going to look like? I don't know. You see the problem for distortion? It's going to be a bit more complicated than just current swing. Nevertheless, we're going to try to get through. Huh? Okay. So another one that's interesting, which is documented well, is that if you go halfway around IC1, where is IC1 here? IC1 is around VT, a little bit higher than VT. IC1 is there somewhere, a little bit to the right, here. Well, if you look at there at the current, we know that indeed we have weak inversion on the left, which is an exponential. I'm sure you remember that. I even used the same colors. Huh? And you have the blue region on the right, which is velocity saturation, going to constant GM. You see they have inverse. They have an inverse curvature. This one goes like this, an exponential, and the other one goes like that. Different nature. So that means that if I take the second derivative of GM, is the third derivative of GM, is the third derivative of the current, this corresponds to third order distortion. That means that if I take the second derivative, this goes to a maximum. And the third derivative of this one, the second one of GM, I go to 0. There is a 0 distortion point nowadays around VT in all sub 65, 130 nanometer transistors. Because indeed that 0 distortion point, of course, is not an easy one. You have to maintain your transistor somewhere in the middle, right on this point. But you can do that with replica biasing. People are doing that in communication circuits. And of course, if you swing hard, the amount of distortion you get from the blue region is different from the amount of distortion you get from the red region. Red is exponential and blue is kind of smooth. So to have a perfect cancellation is not so easy, but it is used. So simply looking at one transistor, the whole story doesn't stop by saying that it should have been a square law. And the exponential one I'm going to cover when I talk about bipolar, of course. Okay, so there is more. There is a inherent cancellation point. Of course, it's not as nice as I show here. Huh? When I look at the real transistor in 65 nanometer, you see the red part and the blue part are really having a very sharp crossover here. But here is a reference, an early one. There are more people saying that I would like to work in this 0 distortion point, where the curvature of weak inversion compensates the curvature of velocity saturation. You may want to do that. 0 distortion is attractive. If you see what the alternative is. Okay? Now, if I take two devices, I know that I cancel all the even order distortion. Why is that? If I take two devices, like in a differential pair, or like in a current mirror, yeah? If I take two devices, you vaguely remember that when I take a differential pair, I have a saturating characteristic. It's kind of a limiter in both directions. Huh? And as a result, all the distortion generated by going this way is compensated by the distortion going this way. You cancel the DC level, indeed. The output of a differential pair, you don't have a DC level there. Like this, common mode, yes, but not differentially. And I cancel second order distortion. And as a result, the distortion on one end is the same as the distortion over there. So I only have third order distortion. This is called compression. Compression. It's very, very, very linear for a small signal, of course, because then this is very, very linear. Do I have a power series to explain that? Of course, I can derive that, sure. Don't I have any second order? Second order would only come in if I have mismatch. If your zero line is here instead of there, then I have a bit more of this than there, and then have second order distortion. So in all those differential amplifiers and filters and sigma-delta modulators and so on, second order distortion is used to figure out how much mismatch you have, because it's the mismatch that causes it. Okay? And normally the mismatch gives you second order distortion, which is usually much lower than the third order one. And when I talk about low power sigma-delta modulators, I'll show you the second order, and it is smaller than the third order one. How much is the third order one? What is the expression? You remember the expression? I've shown it to you. The current swing is going to be the input voltage, the amplitude of the input voltage, the differential input voltage. This is a reference voltage, which is Vgs minus Vt. And then 1 minus, here is the 1, you see. If this were negligible, I would have a perfectly linear amplifier. The perfectly linear amplifier is what I get here. This is the perfectly linear amplifier, but you see that at some point I have to subtract something. It's a perfectly linear amplifier from which I have to subtract something. Okay? And I have an expression only to the maximum, and this is not included. It's only up to this point. So here it is. I have a perfectly linear amplifier and I have to subtract something which is square, law with a square, etc., etc. Okay. Now if I take that, here it is again. If I take the U, and what is U is the relative current swing. Where is my current swing? Here it is. It is the peak value of the differential input voltage scaled by Vgs minus Vt. The peak value of the differential voltage, not half of it, the full one. That's why there is a full Vgs minus Vt is this. And then I find a power series. Easy to derive with squares and this, because square root this is 1 minus x over 2 power series. So the ratio 1 over 8 and the 3/4 gives you about 1/10 of the relative current swing. If I take a differential pair and I swing the current 10%, I need a voltage for that. I can calculate with gems and so on. If I swing the current 10%, if this is 10%, this is 1. 10% is 0.1, this is 0.01, this is 1%, 1/10, I get minus 60 dB. For 10% current swing in a Morse differential pair in the square law region, I get minus 60 dB distortion. Is that okay? For most people, yes. Maybe this is a good time to calculate what's the IP3. IP3 is of course proportional to Vgs minus Vt. The larger I make that, the better that is. If I make that 1 volt is out of date. Nobody uses 1 volt. If I use 200 millivolt, for example, 200 millivolt, 0.2, I get 0.66 volt. 0.66 volt IP3. Okay. Later on I'm going to do something about that. Feedback is going to reduce that, but I can use feedback by using a transistor. This is another transistor. This is a new slide. I just did that calculation a little bit. To show that indeed, if I put another gem in there, 2 transistors together, I find that indeed that my scaling factor goes up. Scaling factor, what was that again? Scaling factor? The scaling factor, it should be on here somewhere. The reference voltage. The reference voltage is, oops, should be. This is the reference voltage. I should have written that on there. Reference voltage is this. Okay. A reference voltage is that. But it says on the next slide, the reference voltage is Vgs minus Vt. If I put another transistor in there, I get a larger reference voltage. This is the gem of this transistor, this is gem of that transistor. If both are the same, I simply get something more than this. That's not much. Putting in another transistor there is not making a big difference. If both have the same GM, because then I get 1 plus 1, this is only 2. That this is larger. A factor of 2 doesn't make a difference for distortion, no. But if I do cross coupling, put a negative resistor there, I've used that to increase the gain. And who raised that question? What does that do for distortion? Well, what it does for distortion is that, yes, if I make that 1, I get an oscillator. So don't go that far. If I make that smaller, like I make that, for example, 0.7 or something, the 0.7 is going to increase the gain, but then your reference voltage goes down and your distortion goes up similarly. Gain usually increases together with the distortion. Distortion goes up together with gain. All those increased gain tricks, and I'll show you some more later on, do increase distortion. Your reference voltage Vgs minus Vt is going to get smaller as a result of that. Okay? Now, what alternative do I have? That's all I can do. 1/10 scaling factor. I can use transistors in the linear region. Yeah. Many people say, gee, that's a complicated presentation. I'm going to go to the linear region and then forget about all that. Yes, it's perfectly linear. Linear region means small VDS, smaller VDS. Huh? Linear region, because linear is a term used so often, means in the corner. Huh, there. Small VDS. Huh? Linear region. Okay. Well, it's perfectly linear for 0 VDS, but 0 VDS is too small. Nothing comes out of there. So I have to make it a little bit, 100 millivolt, 200 millivolt. The more I stick to 0, the more linear, and the more I deviate from 0, like 100 millivolt, 200 millivolt, 300 millivolt, 400 millivolt, the more nonlinear it's going to be, and that's the compromise. For very small VDS, there is a 1 there, no more a 2, and this is perfectly linear. And that's why more and more filters, I'll show you next week in the comparison of the filters, a nice category of filters, all use as a transistor with nearly 0 VDS, 100 millivolt or 200 millivolt. Okay, very low distortion. And that we will have to wait corresponding to feedback to make the distortion smaller. Are you going to make the transistor in the linear region, or are you going to use feedback? Such a simple question. Why isn't there a simple answer on that? Using a transistor in the linear region, this is old, huh? And putting a resistor there, come on, this is local feedback, this is as old, huh? Which one is the best? Next week. Huh? Next week. Today, only distortion. In bipolar, why is bipolar important for you? It's like a MOS transistor in weak inversion. What's the difference? The difference is that there is an N there. MOS transistor in weak inversion. The N is 1.2, 1.3, nonlinear, but the nice thing about bipolar, yes, the nice thing about bipolar is that there is no N. Okay? Yeah, the T I'm going to use for loop gain, so that's why there is an E with the T for temperature. Huh? Yeah, the T is used to, it's also used for time and for temperature and for loop gain and for, unfortunately, but this is just an exponential, as you can see. There is a lot of ingenuity and physics in there. When I talk about band gaps in 2 weeks from now, I have to decipher what is in there. Okay, but I don't have to do that today. This is just a constant, just an exponential. Weak inversion, there is an N, bipolar there is not. And of course, this is heavily nonlinear. An exponential is the crookedest curve of all of them. It's more steep than any other one. More steep than the square law one, than the third law one, and so on and so on. It's very nonlinear. So when I take the AC component divided by the DC component, this one divided by this one is the current swing. If I take that out of there for a DC and an AC voltage, I get of course a power series, and a power series which is very rich. It has all components in there. An exponential has a very long power series. So the 1 drops out because of this, so the Y is going to be equal to this, and I can easily figure out the second and the third order distortion. So this time we have both. In weak inversion, yes, we have IM2 and IM3 because it's exponential. And now we can calculate both of them, and of course the scaling factor now is only KT over Q, much smaller than VGS minus VT. So a bipolar transistor or a MOS transistor in weak inversion is a beautiful source of distortion. Beautiful. That's the problem. So we'll have to do something about feedback or something, because the KT over Q, even with the N in there, it's still only, it's not 26 millivolt. With the N, it's something like 30, 35 millivolt. 35 millivolt is a lot smaller than VGS minus VT, which I can make larger. Huh? So distortion is terrible in a weak inversion MOS transistor. Okay. So if I try to swing my transistor a little bit, rather than to impose a large voltage, this is not going to work. Huh? I overdrive my transistor. I can still calculate that, but I end up with Bessel functions, and I don't want to do that here. No Bessel functions. Okay. So if I don't drive it so hard, I simply see how much I need to get a 10% relative current swing. For that, I see I only need something like, look at this, 1.8 millivolt RMS. And I have already 10% current swing. It's because the gain is so high. In MOS, in weak inversion, that will be 1.3 times larger. That's something like 2.2, 2.3 millivolt. So if I apply 2.3 millivolt to a MOS transistor in weak inversion, I swing the current already 10%, which gives me already, for IM3, which gives me already something like, how much would that be? Minus 60 dB, a little bit worse. Minus 55, minus 56 dB. Minus 56 is not all that impressive for 2.3 millivolt at the input. Distortion is enormous. We have to do something about that. Okay. And now in the differential amplifier, let's do differential and have a break. Huh? In the differential amplifier, we have two exponentials connected together. When you connect the exponentials like this, I get a tangent hyperbolicus, or a tang function. Okay. Since each exponential, that's what you get with the differential pair. Since each exponential has a power series, the whole thing has a power series to 1/3. And when I put that in my power series, I get this. How much do I get in my intermodulation distortion? 1/4. MOS was 1/10. Bipolar and weak inversion is 1/4. So that means MOS is more linear. Because in weak inversion bipolar, you have an exponential is less linear. It's about 2.5 times less linear. 2.5 times less linear. Yeah. My IM3 for the same current swing in weak inversion and in the bipolar transistor, the IM3 is 2.5 times worse for the same relative current swing. Huh? Maybe that's worth remembering. I don't know. So weak inversion is always worse. So that's why receivers still stay in strong inversion. They have a large VGS minus VT. Low distortion means strong inversion, not weak inversion. But yeah, people try everything. Right? Let's have a break now. And then we will continue adding feedback and looking at some more circuits. Right? Let's have a 15-minute break. Is that sufficient to recover? So that's what we got with differential operations. So we are very lucky that we don't have even order, huh? Only third order. Now this is also applicable to other components. I'm not saying that the transistors are the only sources of distortion. No. There is more. Huh? For example, a resistor. If I have a resistor like simply a diffused resistor like this, which has two contacts, and which has a depletion layer. For example, for N-well, and this is P for example. Well, if I have a signal here, clearly the width of the depletion layer is going to change slightly with the amplitude of the voltage on one end. That means that the resistor from one end to the other is going to change depending on the signal. That's distortion. Difficult to calculate, and you see that it's going to be very small, but some people really fish for very small values. Huh? The best way to figure that out is to see that as a junction FET, because indeed the junction FET, this is the gate. Huh? For a junction FET, we have a certain resistance here. If I change the voltage, then the cross section is going to change, and the current is going to change. That means that indeed we have a very large voltage to pinch that off. A junction FET means that I apply a voltage here so that this is pinched off. So we have a very large VT because normally you can never pinch that off. There is too much resistance left, too much conductivity left here in the junction FET. I can only change the depletion layer a little bit, so the VP or the VT is the same thing as very large. And that's because of that the distortion in JFETs is so small. They have a very large VT or VP. And then when I work, for example, when I work at the very, they have a characteristic like this. When I work around this point here and the VP is very large, I can only work around smaller values of the VGS. That means that they have a very large VGS minus VT and the distortion is very small. And that's how you can calculate the distortion of a resistor. Those are very small values. Same with capacitances. I don't know whether I have included capacitance. No, I didn't include it. Sometimes I put that in there. It's clear that if you have a capacitance which is a junction capacitance, that you're in bad shape. When I plot the capacitance versus voltage for a junction capacitance, then in the forward direction it goes real high and it goes like the square root in reverse bias, something like this. And the reverse bias here, for example, the capacitance changes. And if you give me an expression of the capacitance versus voltage, then of course you can calculate current swing and things like that. You can calculate how much distortion we get. Clearly you shouldn't use them. For poly to poly or metal to metal capacitances, this is about 0. It's never really 0. It's about 0. And it's only if you want to go below minus 90 dB, minus 100 dB, minus 100 dB. Phew, what numbers, If you want to go below that, you may have to check what capacitors you want to use, and especially what the resistance is. Those are then poly resistors, and those are the metal-to-metal capacitances, of course. Okay. Why is that important? Well, if you have a beautiful amplifier without distortion, those are the feedback elements, so they will be the most important elements for distortion in a feedback circuit. So it's time we have a look at feedback, what is going to do that to you. Feedback is going to improve things, Sure. Why? Because the current swing goes down. What does feedback do? Two things. If I apply a certain voltage to a circuit and I have feedback in there, all the currents go down. That's what feedback does. And on top of that, we have still some distortion as a result of the current swing in there. So we always have two effects in there. I'm going to repeat that 10 times. When you have feedback, there are two effects. You reduce the gain, and as a result, the relative current swing. Okay? And then at that current swing, you will have, at that current swing, you have a certain amount of distortion. Okay? And on top of that, this distortion is reduced by the loop gain. All books on feedback, all chapters on feedback start by saying we apply feedback to reduce distortion, and sometimes they say noise, but that's wrong. Distortion and nonlinearity. But then how much does it reduce? There are two reasons. First of all, if I apply feedback, the relative current swing goes down. I could say I keep the relative current swing and increase the input voltage. Sure, then I have the same relative current swing. Which one gives you the lowest distortion? The one with feedback for the same current swing is going to give you less distortion. It is the distortion divided by the loop gain, not squared. Okay? The nonlinearity goes down with the loop gain, not the loop gain squared. Sometimes you will see a square, sometimes you see a square, sometimes you see a tree. Sure. So let's have a look at that. Here we go. First, I would like to figure out the effect of the feedback F, realized by means of some resistors or capacitances or whatever. And here is my original nonlinearity. My original nonlinearity, and the question is, how is my nonlinear circuit going to end up with factors, with coefficients D1, D2, D3? And the first one, I know, and I've put on the slide here how you figure that out. I keep on having some emails saying, how did you actually do this? Well, of course, you see that the U here is the difference between those two. And the F, Y times F is this. Y times F is this, and this is the U, and the U has a power series to go over there. The U has a power series to go over there. Okay, and I can take the U in there, okay, and then I eliminate this and I do this. Okay, and then I find the coefficients. Sure. Playing around with equations. Great fun if you're interested in distortion. Now the first one we know, of course. Why do we know the first one? Well, you all know that the gain goes down by means of the loop gain. And the loop gain is what? The loop gain is actually A1F. A1F is the loop gain. This one goes down by means of the loop gain towards D1. So the first one is obvious. Sure, the first one is obvious. That we know because of feedback theory. It's the original gain divided by the loop gain, and the loop gain I've called T. I shouldn't have done that. I should have called that LG or something. Maybe at some point I'm going to change all that. Anyway, the loop gain is always larger than 1, otherwise you can't talk about distortion. Okay? Never take a loop gain less than 1. What does that mean? So larger than 1, that means that A1 is divided by T, and T is nothing else than A1F. And A1F, you get F, and that's the idea. So that your feedback circuit only depends on the feedback elements, which are normally much more linear than this amplifier. That's why I don't like people putting amplifiers there and there. You just go from one nonlinearity to another one. But yeah, maybe there is a good reason. Okay. So this is normally just resistors and capacitances to reduce the nonlinearity of the amplifier from A1 to D. So this one is well known. And now let's have a look at D2, and let's have a look at D3. Okay. So here D2 is like this, but we are not interested in D2. Well, we will be at the end, because if I look at D3, I see that D3 is a result of two loops. Not only A3 going around once, but also A2 going around 2 times. A2 going around once, 2 times. Going around 2 times. Because you see that since my nonlinear amplifier generates third order, I can also have second order generating third order. Because in the beginning it's only a fundamental that gives me third order. This one gives me third order. So if this one goes 2 times, the second one also generates third order on top of this one. And that's why in feedback amplifiers it's easy to have a null, a zero, that this one compensates this one. Feedback amplifiers, when you look at distortion, they have zeros in there. Very sharp zeros. Tons of papers explain how to stay in a zero, but that's difficult. Matching and so on and so on and so on. Okay? So normally you won't count on that. You just apply a lot of feedback T. And depending on whether your circuit has A3 or A2, this one is dominant or this one is dominant. Okay? Making that zero is too difficult. I'll show you some examples, but that's going to be too difficult. So actually what we have in there now, and this is to explain that we have two effects. Two effects. The first one is the loop gain goes down. Sorry, the current swing goes down. And on top of that, so when I look at a circuit, I look at the current swing and all the transistors. I look at the current swing, and then I calculate the distortion with that kind of current swing, whether it's differential pair, singlet, whatever. Okay, and then I divide that by the loop gain. So who is going to win? All transistors are nonlinear. They have some coefficient. We calculate the coefficient, but those are all similar. So the only circuits that are going to be very linear are the ones which have a lot of loop gain, because loop gain can be 10, 100, 1,000, 10,000. Those are the ones with a lot of loop gain around them that are going to win. So actually what I have here is two things. First of all, we have here the effect of the reduction of the current swing. Is the reduction of the current swing itself. Here it is. The V is going to be divided by the loop gain. And on top of that, the distortion is going to be divided by the loop gain itself. And this is why sometimes you have a square. There is one belonging to this and one belonging to the other side. And that's the rule we are going to use. It's easy in a circuit in those filters next week, for example, we are going to do that. You look at the relative current swing, and then you calculate the loop gain, and you divide, and that's it. That is just for Spice, Spectre, and so on. So that's applicable to both of them, also for this one, which is more of interest to us. We have two of them. The one with the plus sign is compression. Why is that? Because if you take a sine wave, and I take the 3 times the sine wave, this is the third order component. You see this one is subtracted from this one. It's going to be a little bit of flat. So the one with the plus sign makes it flatter. That's compression. And the one with the minus sign is going to give you expansion. That means that this is going to be a bit higher. Okay? And expansion can compensate for the compression. Okay? you see that indeed also here the reduction of the current swing is squared now, because the input signal for third order is squared. And now in the rest here there is only one T. Here is 1 and here is 1 too. Okay? So you first look at current swing and then you divide the distortion by the loop gain. And we can try to figure out which one is dominant. A few examples. For example, just a MOS transistor. Can we apply feedback on a MOS transistor? Of course, you can put a resistor in there. For a MOS transistor, the EIE3 is 0. You only have this one here. Okay, that's obviously. And bipolar, you have all of them. Which one is dominant? This is always larger than this one. Also in the transistor in weak inversion, this one is going to be more important than this one. In the differential pair, for example, in the differential pair, this one is 0, differential pair. If I apply feedback to a differential pair, this one is going to be the most important one. So depending a bit on what you're talking about, you have a different combination of those two, but they're always in there. For example, if I take just an emitter resistor in a bipolar transistor, okay, this is the loop gain, and I can calculate things. You see that indeed when I apply feedback, GMRE in a bipolar transistor, and if you have larger resistors, you can do that in a MOS transistor. Currents are so small maybe that the resist has to be large. Then clearly the signal swing in the relative current swing, which we had originally, is going to be divided by the loop gain. That's the only difference. And then on top of that, the loop gain, that's the one. The current swing is going to be divided by the loop gain, and on top of that, this goes down. Okay. And similarly for IM3, note that this, you see here the relative current swing is small again. That goes in there, comes in 2 times, and here we only have 1 T. Distortion, everybody is right, distortion is inversely proportional to loop gain. Third order distortion is inversely proportional to loop gain, not loop gain square. The rest of the story is in the current swing. That's why the current swing is the value that you have to look at. Otherwise you get confused. So many different equations are used in distortion. Hard to figure out. But if you look at current swing and just 1 T, you're in good shape. Okay? And I can, for example, take a transistor with a resistor, and you see that if I look at IM3, there's going to be a null there. Too many papers look at this. When you do measurement, people then say distortion is, for example, 10 dB less because you're on this end or you're on this end. You never dare. At low frequency, you can measure really low, but at high frequencies, you never have that. This is something like this, because some other effects are coming in. I'll say something about frequencies later on. So don't try to get into one of those zeros. That's too difficult to do. And here is one of my favorite things when I'm teaching about noise and teaching about gain and teaching about distortion. Yes. Remember what I've asked you a long time ago? If I take a transistor with the same current as the other transistor here, the same DC current, but somehow I have taken a larger VGS minus VT. A larger VGS minus VT means that for the same current, the size must be smaller, because the current equals K prime W over L VGS minus VT square in the square law region. So if I make the VGS minus VT smaller, I can leave some voltage there. I'm going to do that with the band gaps all the time. I'm going to do that for the band gap references all the time, having 2 transistors with different sizes. And the difference in VGS is taken up by a resistor. And that's going to be a p-tat voltage there, but that's for later. Now I'm only interested in gain, noise, distortion. Okay? You may have the impression that because of the high VGS minus VT, you generate less distortion. High VGS minus VT was the scaling factor. You generate less distortion. But here you have more distortion because this is smaller, but then it's reduced by the resistor feedback. So which one is better in terms of distortion? They're just about the same. Something to think about. Okay. That's true for gain, that's true for noise, that's true for... So actually, playing with VGS minus VT is actually taking in and out channel resistor from the transistor. If you leave more in there, you have less distortion. If you take more out, you have more feedback. Seen externally, it seems to do more, but you generate more, and it's compensated by the feedback. Same thing, nearly the same. So that's going to be the trick I'm going to use next week for all kinds of filters, just to whet the appetite a little bit. I've put in a few. This is what people do all the time, local feedback to reduce the distortion. I'm amazed that this is still today the main trick to reduce distortion. And yet, what is the problem? The problem is that you need an enormous voltage drop there. Okay? A voltage drop where indeed the GMRE means that you need a large GM and a large resistor, so the DC voltage drop is large. Of course, this is a lot better, because now I don't have a DC voltage drop, I only have an AC voltage drop. So whereas for AC it looks very similar, this is much easier to do on lower supply voltages, because here I need a fraction of a volt to have a real reduction of the distortion. You see that the T factor, the GMRE, the GMR there, is going to help to increase the IP3. Sure, there it is with the 3 seconds again. And yes, and the same thing here. So this is a lot more attractive, but it's amazing that this is still the main trick to reduce distortion. Okay. Things that we are going to do next week is, for example, add a bit more local feedback. I can say that now we have so many filters that I need to say a few more things before and maybe after. There are so many filters. So you see that indeed we have local feedback, just the resistor. Here is the GMR. But the T is too small. Well, add another transistor to increase the loop gain. This is local feedback. Yeah. I thought I talked about feedback, so you can calculate the loop gain, I'm sure. I'm sure you can all calculate the loop gain. And the loop gain of that is going to generate, and you have first of all loop gain because of the resistor and loop gain because of the loop gain here. Of course you could say, well, this is not enough, I'm going to put a full operational amplifier in there. That's the best. But if you have a full operational amplifier, why don't you make just a fully differential operational amplifier rather than to go through a GM block? I'm not sure that if you know how to make op-amps, make one like that, which is the same as this without the GMs. So to increase the loop gain, you could have done it by just making a fully differential operational amplifier, something that you all know how to do. So this is something for next week. Loop gain is going to help. And here it is, I can do as a second trick cross-coupling. If you want to do resistances, can't I use the internal channel resistance to compensate distortion? Here it is. Okay. I have taken here 2 pairs rather than 1, and I know both of them give you distortion. And I'm going to take the distortion of one of them and cancel it by the distortion of the other one. So I have to take it in the opposite direction. Clearly, this is a famous circuit if the currents are the same and all transistors are the same. This is the Gilbert multiplier. Okay, multiplier, what is this? If the currents are the same and the voltages are the same, then 0 times 0 is a 0 out. That's obvious. But even if I have a signal here, on one end, and I multiply by 0, no current difference, what I'm going to get? I have a current here, but the current here is just opposite direction. The same current flows there as there, but opposite polarity. So if I add 2 currents of the same size with opposite polarity, there is nothing left. This voltage times 0, which is the difference here, is 0. And only if there is a difference here, I can get something out. So the question is now, if I want to do a cancellation of the distortion, what is the difference in parameter here and the difference in current there that I need to do to cancel not the signal, but only the third order harmonic or intermodulation product? So I need the difference between the currents, which is this, that's the alpha, and the difference in size, but I prefer Vgs minus Vt rather than size. So we have 2 parameters to play, alpha and V. Maybe I should have taken alpha and beta, but why always alpha? Whatever. So the question is, what is going to be the difference in current here and the difference in transistor size reflected by the difference in Vgs minus Vt to make the third order 0? That's not so difficult to do. I've given you the expression of the third order distortion of a differential pair. So just apply it. Okay, I think it's on, here it is. Here is the power series for the differential pair. I have one there, and I have one there, but with different VGSs and different, so I have an alpha and a V in there, and here it is. And here it is, and you see indeed there is a condition for which this is going to be 0 when this equals 1, when this equals 1, or V equals 1 over alpha third. Here it is, this must be 0. So 1 equals alpha V third, or V should be alpha minus 1 third. Huh? So now you have to put in some values. Here are some values. Alpha 1 third, if I take a ratio 1 to 4, and here is the problem. How long can you do that with VGSs? So you shouldn't take that too big. Huh? If this is 1.2, the 0.2, the other one could be 0.32, and then have perfect cancellation. It's a 0 again. And if you cancel the distortion, luckily there is some signal left. Huh? You don't cancel the signal itself at the same time as the distortion. There is a distortion cancellation point different from the signal. Meaning that indeed I have several possibilities there. I can take this combination, or I can take this combination, or I can take this combination. I would take the one with the lowest slope. Otherwise, you need better matching. So if this is too steep, it's a little bit harder to do. Huh? A smaller ratio in VGS minus VT is more difficult to do. A larger ratio in VGS minus VT, which is hard to do for technology, is easier to do in terms of mismatch. You would like to be around 0. Huh? Okay. So that's one way, and so many people do this. I like this. Cross coupling, I have advertised here so many times already. Negative resistors. Okay. It was in the last magazine, described by several people. All of a sudden people write about negative resistors everywhere. Me too. Okay. But you can use that to cancel the distortion. Okay. So that's not quite a negative resistor. So here is an example on, this says what alpha you can get. And this shows how many signal is left. 60% of the signal is left. If you cancel all the distortion, then you reduce a little bit the useful signal. You give up 40%, which is not too bad, isn't it? So this is something to be done. Does that work in weak inversion? I just added this. People ask if you are in weak inversion, does that also work? Yes. Surprisingly, the same expression. Why not surprisingly? Because you have a similar power series. It's 1/3 now, not 1/10. But after all, what difference does it make? So if you do that in weak inversion, where more and more of you are going to end up in, huh? I have to calculate and those things, and here is the expression again. It's the same expression. I went through the whole thing. Since we have the same expression, we get the same condition. Okay. And now the V's are different, because now we have the scaling factor is KT over Q. Okay. This is not so easy to make different, so it's a little bit harder to do, because we are going to have to work with different transistor sizes, which are not expressed by the KT over Q. So the transistor sizes are different here. We don't have a VGS minus VT, but I can make different transistor sizes, and that will help you to cancel the second order distortion. So that's something to do, huh? Now let's take a full-fledged operational amplifier. A full-fledged operational amplifier, yes? And let's have a look at some numbers and some measurements, huh? And look at the rules and some other kinds of distortion. Here is an amplifier. I'm not going to surprise you with the amplifier. Hey, you know all about amplifiers, huh? Isn't it? I have taken a nice one here, 10 to the 4th, bandwidth 1 kilohertz, 10 megahertz, the gain is 10. And I've added a load, huh? Why do I need a load? If there is no current flowing in the output resistors, then the relative current swing, there's no current. If there is no AC current coming out of there, only the AC current for a very large resistor there, then the relative current swing is going to be very small. But we have taken this kind of feedback to drive something. So we have put the load in there. So some current is flowing in and out the transistors. Okay. This could be class AB, I'll come to that. Or class A, depending on how we do things. I first take a class A amplifier, and then I go further. Huh? So this is an amplifier with a load like 100 k ohms and 5 picofarad for a gain of 10. You know what the loop gain is, and you know what's going to happen. We will have to jump into that circuit and figure out for all the transistors what is the relative current swing under the condition that the loop is closed. And then divide that distortion by the loop gain, and the loop gain is large here and getting smaller and smaller and smaller. So where is the distortion going to be worse? Here, of course, just before the corner. Are we surprised? No, of course not. Of course not. Here we have a lot of loop gain, goes down, goes down, goes down, goes down. This is the discussion today now for filters. Because if I'm going to ask how much is the distortion, well, the distortion here is terrible. I'm going to give you the distortion here. Is that comparable to distortion over there? No. Unless you say that we have so much less loop gain. Because the loop gain makes a difference. And this is now the discussion today for all those filters. People say, if you compare filters, you have to say how much loop gain you have. If you have a figure of merit, you need to put the loop gain is there. This paper will be out in July 2015. It was on SCirc last September. First paper saying we need a loop gain in there. Obviously, how can I compare distortion here to there, even if they are caused by the same transistor? The loop gain makes the difference. Okay? Most people say in-band distortion is beautiful. Sure, but I would like to know how much is here. Well, it's easy. It's so much less. How much is it on the corner? How much is it going to be there? Whoops. No loop gain, and then you have attenuation and all of that. Very different. You know that in-band and out-band distortion is important for all those receivers and all those filters used in the receivers. Well, they should mention the loop gain because that's the main reason why distortion is small. All coefficients in those power series are similar. MOS, bipolar, differential pair, and so on and so on. Okay, but the loop gain makes a difference. Okay. Now here we go. Distortion in a operational amplifier we take with two stages. Well, two stages have different distortion. Are we going to focus on the first stage or on the second stage? When we went through a two-stage amplifier, I did tell you, you have to try to figure out halfway how much is the amplitude. If you drive an amplifier like an op-amp towards an output with resistances, as I've just shown, you have to figure out how much voltage you have there. Okay, you won't find a single paper on this amazingly. The voltage between the two stages of a two-stage amplifier. The voltage between the three stages of a three-stage amplifier. Because if I don't know what the voltage is, how do I know whether this is going to be overdriven or that is going to be overdriven? We need to have the input voltage to figure out the relative current swing, isn't it? Assuming that it's the input stage and the output stage is very linear, what am I going to get? Well, here we go again. We have to go through the analysis. D1, D2, D3. Now, of course, we have a nonlinear stage here, and the B is constant. A stands for the input stage, and B stands for the output stage. A, B, okay. And now we have to figure out the D's, okay. Here we go with the D's, and we have to do the calculation. The D's are given. And with that, we can figure out the IM3, and we'll find some A's and B's in there, but I didn't put in the values yet. So that's one thing. I'll put them together when I do both of them. That's one thing I can do. And then the other thing I have to do is that there is a filter there. Sure, there is a filter. Remember the capacitance? The capacitance, the compensation capacitance, if you have a compensation capacitance. Maybe you prefer feed forward or something else. So there is a low-pass filter there cutting down frequencies. That frequency was a frequency in the middle of my range. I discussed that when I discussed two-stage amplifiers, a few kilohertz or something. So there is a low-pass filter there. What does a low-pass filter do in the feedback loop? A low-pass filter in the feedback loop is used by everybody doing sigma-delta modulators. So you better figure that out. That's 2 weeks from now or 3 weeks. 3 weeks from now. If I have a low-pass filter here, I have a high-pass characteristic on those other elements. It's going to be inverted at the output. So if I have now a low-pass filter characteristic in there, it's going to do something else. Here it is. I have a high pass characteristic. So the IM3, that's the one I'm interested in. The IM3 is going to look like this. All equations. I have this. What frequency is that? That's my 2-3 kilohertz, where the loop gain of my first stage was going to go down. It is the pole in the middle between the two stages. I got 3 kilohertz or 4 kilohertz or something when I looked at the two-stage amplifier. Okay, meaning that indeed, because of all the squares and the thirds, you have a power like this. Comes up very strongly, not surprisingly, starting at the frequency where I start losing the gain of the first stage. So, how much distortion do I get from the first stage? So much. And it goes up. Why does it go up? Because a two-stage amplifier is a filter. Sure, it's a filter. The gain goes down. It's a low-pass filter. It is a low-pass filter. And as a result, distortion goes up. I lose the loop gain. Distortion goes up. Okay. Now I can have distortion in the output stage. Because this may be some signal which is quite large. Because if the gain goes down here, a lot of that signal is going to be left. So if I have a certain signal level there, I may have an output stage, just one transistor. I've said so many times the second stage in a two-stage amplifier is one transistor. Okay? If I overdrive the transistor, we get a lot of distortion. Okay? So now if you look at distortion over there, it's going to be there. A1 is now here, and you see that the power series change, huh? Because now we have a B power series. Okay? We have a B power series. And also the A1 and the B are in there. Okay? And now if you grind through the equations again, we find that actually that distortion is independent of frequency. Because it's after that filter. The transistor at the output of a two-stage amplifier is at the output. Of course there is a non-dominant pole, but this is too far. This is far enough. So that means that this doesn't do any much in terms of frequency. The noise shaping, working on the nonlinearity of the input stage. Noise shaping, the filtering. For sigma delta modulators this is called a noise shaping, but maybe prefer the word filtering. The filtering of in the input stage of a two-stage amplifier comes out as a high-pass filter for the distortion. What happens afterwards in the output stage doesn't do much. And if you combine them together, here we go. Where is the distortion coming from in an op-amp? I'm going to use next week all those op-amps in those beautiful low distortion filters. Beautiful filters. Huh? Am I going to use an op-amp or not? Well, you see that indeed the one, and I put in the non-dominant pole in there. It's still there, huh? The non-dominant pole, sure. But if I look at the basic characteristics, I see the A1, the input stage stuff, in black. And the second stage one, the output stage one, in the red. Okay. I don't know whether you have that. The input stage, it's all the output transistor, of course. It's the output stage. If I go to high frequencies, it's going to be the input stage. Where is the crossover? Is that my 4 or 5 kilohertz? No. My 4 or 5 kilohertz is here. Okay? So we have two independent generators of distortion, the input stage and the output stage. And one takes over the other one, and you're welcome to calculate this frequency. I did that once. I had a slide full of expressions. I thought this is bad enough. Huh? This is already... Okay? So to calculate this frequency, you're welcome to do that. Huh? Okay, I'm not going to do this. I'm going to show you a curve like this, sure. And then you know in this curve you have two regions. Huh? There is a different source working there. This is the output stage. But at high frequency it's the input stage. So if we make low distortion amplifiers later on, I'm going to ask there, or both. Okay? Depending on whether you work on frequencies below this, so maybe we have to calculate that, or above this. Okay? That's for two stages. It's that simple. Input stage or output stage? It's output stage. Let's calculate it. Numbers. You want numbers? Here we go. A few more numbers. I've put in all the numbers. Huh? This is at low frequencies. I'm sure this is nearly an exercise. I'm sure you can all do that. Huh? Because I've calculated here for low frequencies, it's always easier. Huh? At low frequency, the gain is 2 times 100, 100, 100. This is a capacitor somewhere. The gain is 2 times 100. Gain bandwidth like this, 100 times 100 is 10,000. Kilohertz bandwidth, the gain bandwidth 10 megahertz, the gain of 10 closed loop to figure out the loop gain. And then all numbers corresponding to those. Easy to figure out numbers corresponding to those. They call that design. Okay, for a certain capacitance. It's important to realize that the gain is 100, 100 at low frequencies, because then this we have 10 millivolt here. At low frequencies 10 millivolt. Obviously, applying 0.1 millivolt to a differential pair, which gives you less distortion than 10 millivolt to a transistor. So the culprit here is this transistor, of course. At low frequency, it's the second stage, as I've just explained. Can you figure out the relative current swing for 10 millivolt at the input? Yes, you can. Can you figure out the DC current? Here it is somewhere. DC current, IDS3 DC current is 120 microamp. For 10 millivolt at the input, how much AC current do you have? GM times 10 millivolt, relative current swing, power series. And then what are you going to do with it with the distortion calculator from it? Divide by the loop gain. Okay? So here we go. First of all, let me show you that curve again to show you where the 10 millivolt is coming from. Strange curve. Strange curve. Look at this. The 10 millivolt is here. This is my 10 millivolt. Starts going down at the loop gain. 1 kilohertz. Follows it. You see the gain of the second stage is constant. But the gain of the first stage you lose. So by that point, which I didn't calculate, never calculate, and then it gets stuck to something. For a simple two-stage amplifier to figure out the distortion, a simple two-stage Miller operational amplifier, we all know so well. To figure out the distortion, you have to calculate the blue curve, how much you have in the middle to figure out the distortion of the output stage. Okay? And you see that in the beginning it's going to be the output stage, but then it's going to be the input stage, the gain goes down, and it gets stuck to something like this. The blue curve is this, This is blue, this is black. Non-dominant pole, 30 megahertz. So now knowing those numbers, here are the calculations. At 100 hertz, I've calculated the relative current swing for this transistor. If I apply 0.1 millivolt, I take the expression I've given you before, 0.1 millivolt in a differential pair. Relative current swing is 5. 10 minus 4, 0.05%. That's nothing, Forget it. No distortion there. Distortion here with 10 millivolt, the relative current swing in there is 0.1. It's already 10% with 10 millivolt. Sure. The output resistor provides a lot of AC current in there. If there were no AC current, there would be no current swing and no distortion. You need current swing. If you remember that from today, you're an expert. Most people don't even know this. And here we go. How much is that with 0.1% transistor? Well, the IM2 is 2.5%. Okay, 2.5%. Don't forget to divide by the loop gain, 1000. We get 0.0025%. We all know that. An operational amplifier at low frequencies gives you very low distortion because you have a lot of loop gain. Sure, there it is. Okay? That's not going to last if you go to higher frequencies, of course. Let's take 100 kilohertz. It would be nice to do that calculation for all those frequencies, isn't it? And make a plot. But I leave that to you. Too many numbers, too many equations. I've just taken one. And you see what's going to happen. I still have, now here I lose the gain of the input stage. I lose the gain of the input stage. I lose the gain of the input stage. You see? This is AV1. So that means that my 10 millivolt is also present. My 10 millivolt here I have to apply there to get the same voltage out. Now I have 10 millivolt here, so this is going to go up. This is a lot larger, but it's still okay. Those are coefficients, This is still 0.05 relative current swing because of the larger voltage, because I lost the gain at 100 kilohertz. The main thing there is at 100 kilohertz, the loop gain is so small. The loop gain is only 10. So now indeed there is more distortion coming from the input stage. But the main thing is that the loop gain at that frequency is so small that the distortion has gone up. And it's only when I go to higher frequency that the input stage takes over and I have a steeper slope. Okay? So loop gain, and trying to figure out per transistor where we are, and that's how we get those steep slopes here. So where is that coming from? Those curves here. Where are those coming from? We concentrate on HD3 because there is a single output transistor. There is also second order distortion, of course. When we take all those operational amplifiers fully differential, you can forget about this one. You can forget about this one, and then this one is the most important one. Oop. This one is the most important one. What is that caused by the input stage? And why does it go so much higher? Because the input stage gives you more distortion, and the loop gain mix gives you a third order slope. This is third order. And where does it start? That frequency you still have to calculate. And is that distortion or noise? I don't know. Yeah, once you get to 0.001%, how do you measure that? I don't even know whether this is distortion or noise. But who cares? I think it's distortion because it's not that low. But depending on the currency used, the noise may pop up. Okay? The noise may pop up. Yeah. So how? This is a very important slide. I get stuck on it. Oh, no, don't do that. Thank you. Because I did save. Anyway. A low distortion amplifier. What is low distortion amplifier? You know the result. The more loop gain you get, the lower the distortion. What more can I say? You really want to work on the input stage separately to make that small? Are you going to apply local feedback to the input stage to make the distortion, where was it again, at high frequencies smaller? Are you going to work on this transistor here, because you have seen already this is a two-stage amplifier? Am I going to work on this transistor here to make the distortion smaller? You can. But those are coefficients. The loop gain is so much more important. So what does that mean, a low distortion amplifier? That's going to be an amplifier with a very high loop gain and thus a very high bandwidth. Unless it can have a lot of loop gain without bandwidth. That means a second order amplifier. And then you have to talk about stability. Okay? So this is very simple in the sense that this is a beautiful amplifier. Look at this. Huh? Beautiful amplifier. Yes, indeed. Yes, indeed. This is so high because I need low distortion. Be careful for audio and other application. You may also have slew rate enhanced distortion. Nobody talks about that anymore because all our amplifiers have so beautiful slew rates. We have improved our amplifiers slew rate versus gain bandwidth because we have taken large VGS minus VTs in there. Remember when I talked about the design of a two-stage amplifier? You take a large VGS minus VT. Couldn't care less about noise. I need a large VGS minus VT for a large slew rate, or I'm going to add some resistors there. Even worse for noise, but even better for slew rate. So the slew rate is large, and as a result I don't have slew rate enhanced distortion, which is what? Then your sine waves become triangles. There was a time that all audio amplifiers suffered from that, because we couldn't make an op-amp with a large slew rate, but now we can, and this has disappeared from the scene. People still love triangle sound, gives you some distortion. Many kinds of distortion are nice to hear. Okay, so don't think distortion is bad. Huh? No. Sometimes distortion is nice, huh? And that's why this is a bit larger. This has a large VGS minus VT for low distortion, and this has a large VGS minus VT. What does that mean, large VGS minus VT? For all the GMs, you would like to have that means large currents. Huh? So again, low distortion means large current. Huh? I put the current in there to show you. Huh? No, we are not yet in the power electronics kind of presentation. No, but look, 25 milliamps. What are we talking about? Maybe you prefer 25 nanoamps. Huh? Okay. Low distortion amplifiers are high power, high speed for the loop gain. the coefficients are not so important. Nobody puts in the resistance there and there. It's not worth it. Okay? It's the loop gain that makes the difference. Okay? So what I have done, well, it's a time has come to summarize a little bit. Huh? The limited slew rate I have left out. You find lots of literature on the triangular waveforms. I don't think that's important anymore because we know how to make large slew rates. That kind of distortion. A switch, for example, I didn't discuss either. Because what kind of distortion do you have if you do this? Through zero. We did that actually, isn't it? But not around zero. If you have a switch here, which you are going to switch close to zero, that means that you go positive, negative at this point. Not much. Huh? You don't want to go too far. So that means that source drain exchange all the time. And then you have distortion because you go through zero. I will say something about that next week. Because you have this characteristic. This is the characteristic of the switch. If it's very linear around zero, but if you go too far, you have third order distortion, as you can see. Which we can actually handle if we have this characteristic, and we have. So this is something for the MOSFET C filters next week. I'll talk about that, yes. So this is for switch or CS, switch. Okay, that's for next week. High frequencies. I said several times, well, it's easy. Hey, you calculate the distortion. Either it's generated after your filter or before your filter. If it's after your filter, it's not effective for the filter. If the distortion is generated before the filter, then the filter simply is applied to the spectrum of that filter. That's not quite true. There is an interaction between frequency behavior and the generation of harmonics. And as a result, we need Volterra series for that. But I don't do that anymore. I did that in the 70s and in the 80s. It's too complicated. Nobody is listening. And the nice thing about that is, first of all, it's very complicated. And if you just take power series and a filter after, you have a bit too much distortion. You're on the upper end. Okay? But if you really want to know the exact value, and there are papers in the Journal of Solid-State Circuits with Volterra series. Okay? You're welcome to have a look at them. Okay? I did that too some time ago, but it's too complicated. It's much easier to work with figuring out you generate distortion and you apply a filter to it. And the IM3 is close to the fundamentals. Okay? If I have a low distortion filter and I have a filter just after that, the harmonics are gone, but the IM3 is still there. That's what the advantage. Okay? That I'm going to cover next week, because if we want to compare all those filters, sometimes I talk for half a day about continuous time filters. Next week it's just 2 hours, not more. Then we have to have the distortion, all of those. Do we have that? No. Some work to be done and guidelines. So half of this slide is for next week. And finally, how do you do that? Well, the most important thing is the current swing and the loop gain. But of course, I can't stop you from trying cross-coupling. People do use that. Okay, if you have matching and you have cascodes everywhere and the VDSs are about the same, works fine. If not, hard to do. Of course you will do that. Can you imagine a filter today which is not fully differential? This is over. Huh? Cross-coupling helps, but the two main tricks are those. It's amazing that people don't like cross-coupling. Huh? And voltage, I'm not sure what that means. Your transistors are current-carrying devices. It's the current in there that makes a difference. Too many papers are talking about voltage drives, but you have to convert that to currents. It's the current swing that matters, not the voltage swing. Okay? So what is the table putting it all together? Here it is in 2 slides. Huh? To convince you that those coefficients are not the main thing, the loop gain is the main thing. This is a summary of everything I've said, except for the cross-coupling, saying that without feedback, and this with feedback, without feedback, for example, a MOS transistor, how much distortion is going to MOS transistor give you? Well, if I'm interested in IM2, for example, it's 1/4 times UP, the peak current swing. Okay, and the peak current swing is the peak input voltage divided by the reference, and the reference is this. You see how to read this table? This is a summary of all those numbers, huh? Okay. For a differential pair, for example, how much distortion is generated by a differential pair? It's 1/10 of the UP squared. And UP squared is UP with a reference. The reference is there, is this. Input voltage divided by a reference. If you don't have cross-coupling and things like that. And the reference is this, Vgs minus Vt. It's different by a factor of 2, yes. And now if I add feedback, all of those go down by loop gain. Isn't it? Here we go. Look at this. The difference between those two. And where do you find loop gain? You find loop gain 2 times. You find loop gain not only in the relative current swing. All of them have T just once. But this could be squared. And on top of that you have another T. You see, you have another T. 2 times T. If you understood that about T reduces the relative current swing, and on top of that you divide the distortion by the loop gain, then you are an expert in distortion calculations in circuits. We will apply a lot of that to all the filters next week, because we have a whole bunch of them. Okay, some of them use op-amp, some of them use local feedback, some of them use this, some of them use that. But then I will use those 2 slides here to figure out distortion in some of those amplifiers. So ladies and gentlemen, this is what I wanted to explain. The thickest book you can find on the distortion is this one, where you have all those coefficients for one transistor. It's a thick book, be careful. And of course some other things have been published before. This is an expert. Lots of people are doing, those are doing the distortion on 3-stage amplifiers today, figuring that out. Yeah. Those are 2 people, yeah. They're still together, huh? Those are the people in... He's here. The one here. Pete. Yeah. He wrote this book before. He went from ESAT to IMEC. He first finished this book. And I'm still glad he did. Thank you for your attention.